We're waiting for the speaker, so when the speaker arrives, we will start the meeting.
Probably session is delayed because the other talk may be going on. I don't know. Anybody has some idea as to why there is delay? Maybe you can send a. Should we wait a few more minutes before we start?
Sure. Yeah. So it was just got over now. I was also there in the other one. Yeah. How are you? You're muted, I think.
No.
Oh, now I can hear. Yeah.
Maybe just 2 minutes because the other talk is over now. We can just start in 2 minutes.
Yeah, no, I was there just now. After it got over, I came here. Yes. So where are you actually?
At home with a virtual background. That's why.
That's why no cannot make out where anybody is nowadays.
Yeah.
So should I try sharing?
Yeah, why not we work that part out at least? Share and.
Is it better to share this or share screen and then do it? I mean, what? Let me see.
Yeah,
I can share the slide, but then if I have to write something, I have to do again.
As you please. I really have no.
Yeah, it's okay. I have shared at the moment just the PDF, but if I need to write something and show, I have another tablet which I'll have to share. Yeah, it's okay.
since a lot of people maybe also on YouTube, there is no point waiting here. So 2 minutes are up. Let's start. So
this one just got over just a minute ago. Yeah.
okay.
So anyway, we can start. That's fine. Yeah.
Yeah. So let's start this session now. So welcome everybody who is joining. Our next speaker is Professor Manjunath Krishnapur. He is at Indian Institute of Science, Bangalore. And his talk is today on KMT strong embedding theorems. Manju.
Okay. Thank you, Rajiva. So can you hear me clearly?
Yes, we can hear you.
Okay. So I have shared this one. So let me make it full screen. So 1 second. Okay. So my talk is on this KMT strong embedding theorems. I once before gave this lecture in the Bangalore probability seminar. Here I'm assuming people are not necessarily probabilists, which may or may not be true. So anyway, let me explain. So, okay, what is this topic about? It is like this. So let's start with the most basic objects in probability. By the way, at any time, please stop me to ask questions and don't ask in chat. I won't be able to see. I may not pay attention. So you can unmute yourself and ask, but in the previous talk, I was not able to unmute myself. So some setting has to be given, I think.
If somebody sends it on chat, I will try to monitor and...
Okay, please, then you can interrupt me and tell me. Okay. So let's start with the most basic objects, namely coin tosses. So XYs are coin tosses, meaning they are equal to plus or minus 1 with equal probability. Okay, XKs are plus or minus 1 with equal probability. And Sn is x1 plus up to xn. So this is what we call simple symmetric random walk on integers. I will show a picture later. Then this is one of the basic objects we study in probability. And let Z denote always, Z will denote a standard Gaussian random variable, which has density e to the minus half x square with this normalization constant. So one of the most well-known theorems in probability, which we study in basic probability class, is central limit theorem. And this you study even without the general situation. For Bernoulli random variables, we study it in basic probability. So central limit theorem, what is the statement? It is that Sn by square root n converges to standard Gaussian, which can be written in another way, slightly unfamiliar fashion, that you can couple this random variable Sn with Z such that probability that Sn minus Z square root n is bigger than x square root n goes to 0 for any x positive. So it's just another unfamiliar way of stating it, just makes it more clear for the other things. So this is, if you divide out by n, it tells you that Sn by root n minus Z bigger than x, that probability goes to 0 for all x positive. So that means you can couple. What is coupling? Coupling means you can construct one random variable having the distribution of Sn, another random variable having the distribution of Z on the same probability space. So they would have to be dependent on each other in some way, and then this will hold. Okay, so this is a basic central limit theorem. So in that sense, you can couple, informally you should think that you can couple Sn and Z square root n. We have to scale up by square root n because Sn has mean 0 and variance n. Because Z has mean 0, variance 1, so you have to scale up by square root n. So after you scale up by square root n, so these are two random variables with mean 0 and variance n, or standard deviation square root n. So they are of, the difference is of order little o of square root n. That's how we should think, because x can be arbitrarily small. This difference is of little o of square root n. But is that the best you can do? Can you do better? Actually, much better. In fact, this is the topic of this one. I mean, this is a known fact. This is not a new theorem that I am telling. But what is the main point here is that you can do much better. You can do a coupling such that Sn minus Z root n bigger than even x. Okay, so this is some universal constant C, 10 or 100 or something like that. Probability that you can couple them such that the difference is bigger than Cx decays exponentially fast in x. This doesn't depend on n at all, you see. So this is telling, this is far better than the CLT statement. So what it is telling is that these two same random variables which have variance n and mean 0 can be coupled in such a way that their difference is of order 1, right? Because here you don't have x root n, you just have x. So you can make this e to the minus x arbitrarily small by taking x large. So you can, they are of unit order, roughly speaking, that's how you can couple them. So this is the fundamental theorem about which we are going to talk. But why do we care for this theorem? So the reason is this comes up in what is called the KMT theorem, which is in the title. Okay, so let me explain that. What is the KMT theorem for simple symmetric random walk? So it is a similar theorem to this, just at a functional level. Okay, instead of sums of random variables and comparing to Gaussian, we are going to compare random walk to Brownian motion. Okay, so before that, let me show you a picture, a very crude picture. This is a random walk. Each step, it goes +1 or -1. So this each one of these is a step. So it goes either -1 or it can go +1 at each step, and it's decided by a coin toss. And this is what a Brownian motion is. This is not the time when I can define Brownian motion. So I'll assume that one is familiar. So strictly speaking, okay, in my talk, if you don't know what Brownian motion is, you may not understand the statements, but you can still understand the proof. Okay, I will explain that later. So if you don't know Brownian motion, still hang around for a while, maybe you'll get something. Okay, so let's take a simple symmetric random walk and let W be a standard Brownian motion. The famous theorem of Donsker says that after time-space scaling, S converges to the simple symmetric random walk converges to Brownian motion, which can be stated in the following way, that you can couple these random variables S0, S2, etc. up to Sn with the Brownian motion at times 1, 2, 3 up to n in such a way that if you take, it's exactly like we took before, Sn minus Z root n. See, this Wk has exactly the same distribution as square root k times Gaussian, but Wk's are not independent. So what we are taking is the Brownian motion at times 1 to 0 to n, random walk at times 0 to n, and we take the maximum difference between the two. So which should be thought of as how can I couple this random walk path with this Brownian motion so that the total difference between the paths, subnorm distance between the paths, is small. So Donsker's theorem tells you that the probability that this is bigger than x root n goes to 0 for x positive. In other words, that's the same as saying if after time-space scaling, simple symmetric random walk converges to Brownian motion. But here is the famous foundational theorem of Komlos-Major-Tusnady from 70s. It builds upon many other works. I'm not going to recall the literature much here, but it builds on earlier works of, after Donsker, there are works of Strassen and Skorhord and others, and it builds on that. What the basic theorem says that you can couple them, the simple symmetric random walk and Brownian motion, up to time n, such that the subnorm between the two is not of order square root n, but only of order log n. So in other words, the subnorm bigger than constant log n plus x is already, you have a uniform bound e to the minus x. In other words, the difference can be only log n big. Okay, so that's how close random walk can be coupled with Brownian motion. So up to time n, you can couple them so that they are within log n of each other. This improves on the square root n in Donsker's theorem. Okay, by the way, I'm assuming everyone can see the cursor. I'm not using any highlighter to do this. So where I'm pointing, is that being clear or not? Is okay? Okay. So this theorem improves on the square root n in Donsker's theorem. Instead of x square root n, we have only log n. So, but it is not as good as this. It's not big O of 1, but it is log n. Okay, so it gets worse and worse with n. So Komlos-Major-Tusnady did not just prove it for Bernoulli random variables, but random variables with exponential tail, IID random variables with exponential tail. And later it was generalized to various other things like non-IID case, multivariate situation, and so on. Okay, any questions, comments on this so far?
None in the chat as yet.
Okay, fine. Okay, so then let me just, what I want to give is some outline of the proof strategies and what the proof is like. Okay, so so this is a theorem from 70s, what Komlos-Major-Tusnady did. So there are two proof strategies largely. One is combinatorial. I'm just calling it for to be clear about the difference. One is I call combinatorial, another I call analytic. The combinatorial proof is essentially what Komlos-Major-Tusnady gave, and then it was improved by many others. A good place to read it is Pollard's book, this User's Guide to Measure Theoretic Probability or something like that. And Mikhail Lifshitz has a survey article that includes various extensions due to, as I mentioned, Sakharenko, Zaitsev, and many others. So there are many powerful theorems. The analytic one is due to Chatterjee. He did it for simple symmetric random walk. So somehow this theorem is very important, a very foundational theorem in probability, but its proof is generally perceived as somewhat difficult. So people have been trying to simplify the proof in various ways all these years. And Chatterjee, I have not put the years against the names. This was a paper in 2008 or 9. It appeared on Archive, published in 2011-12. So he proved for simple symmetric random walk by a very different method, by what is called a Stein's method, similar to what is called Stein's method. Chatterjee is in fact one of the world's leading experts on that method. So he gave another proof, which I call the analytic proof, and it was extended by Bhattacharjee and Goldstein to more random variables than Bernoulli's. So the general idea in both kinds of proofs is like this. So first one has to prove a theorem like this, a univariate coupling lemma. Okay, so your Sn you have to couple with a Gaussian. So that is step one always. You couple univariate random variables with Gaussians by whatever method. Sometimes, so this is not dissimilar to the very basic thing you see in first course in probability when we prove what is called De Moivre-Laplace limit theorem, which is CLT for Bernoulli's, where what we do is we use Stirling's formula to show that the binomial coefficients with binomial probabilities are close to Gaussian density. This is at a broad level, it's not dissimilar, but you have to go much finer into the Stirling's approximation to get the right kind of bounds. It's a much stronger theorem that you have to prove. So the analytic proof does the same by using some kind of a Stein's method, which is what we'll come to. And then there is a second point, which is you have to go from univariate coupling to the coupling of paths, because the difference between KMT and this is you have to couple so that the maximum difference between random walk and Brownian motion is small. So to do that, what do? You first couple the endpoints, Sn and W, you couple. Okay, so Sn and Wn you couple by the univariate lemma. Now conditional on that, you couple them at the midpoint. Okay, conditional on that, it's no longer exactly a random walk. It's a random walk with a drift, but that's what you have to do. You have to couple it at midway point, Sn by 2 and Wn by 2, but after having coupled these things. And then you again couple it at n by 4 and 3n by 4 and so on. You go on up to, in a dyadic fashion, up to log n generations, and that suffices to couple the entire paths. That is broadly the method. And so that's the general way. Okay, so these are the two broad steps in both methods, combinatorial and analytic. So what, last year I uploaded a paper on the archive where I gave a proof for both the combinatorial and analytic, just taking the frameworks and somewhat simplifying both. Here I will talk only about this analytic method. Okay, I will only talk about the analytic method and what we are adding to it. Before that, let me explain slightly what Chatterjee's approach to this is. As I said, this is a repetition of the previous slide. There is a first step, which is univariate coupling lemma. You have to show Sn, some coupling lemmas have to be shown. But as you see here, it's not simply how do you couple Sn to Wn. You also need to know how, conditioned on Sn and Wn, how you couple Sn by 2 and Wn by 2. If you know that, pretty much you are through. That's the key step. So the second step is this going from univariate coupling to that of paths. And I'm not going to talk about this. We'll not talk about this second step. It's actually the easiest step in a way. I mean, the key, all the difficulty or the main part, or maybe, okay, let me say easier, at least understood. So the key thing to do is this univariate coupling business. Okay. So this is what we'll talk for the rest of the talk, how to do this. So let me just explain what are Chatterjee's coupling lemmas. So it's not enough to have one coupling lemma like this. In the first slide, I showed one coupling lemma like this. This is one of them, but we need one more. As I said, you need to do conditionally too. Okay, so what Chatterjee does is he considers both. So the first one is basically the binomial coupling lemma, which says that the binomial SK0, I have just introduced further notation here, which I will explain in a moment. But SK0 is exactly binomial binomial distribution with k, half parameters. That is x1 plus up to xk. You can couple it with this so that you have this. So, okay, what is the, I just phrase it in a different language, that's all. So what are the two coupling lemmas we need? You consider a box with n coupons labeled plus or minus 1, okay? And let's say there are n plus s by 2 coupons which are plus 1 and n minus s by 2 coupons which are minus 1. Okay, so that so the sum of the coupon labels will be s then. Now, what I call S, capital S sub k comma, sorry, too many S's here, I should have realized, not a good notation. So capital S without the hat is just the sum of k coupons drawn with replacement, which means it's just a binomial random variable with mean which is half S and variance this. So, and S hat, when I put a hat, it is sum of k coupons drawn without replacement. This is what is called a hypergeometric distribution. You don't have to pay attention to the parameters here for the level of detail in this talk. But the point is, these are exactly what come up here. So when I was talking about Sn and Wn, Sn is a binomial and Wn is a Gaussian. That's what you need to couple. That's what is happening in the first lemma. You couple a binomial random variable with a Gaussian. But when you condition on that and look at what happens halfway through, you get into hypergeometric because Sn is fixed. Sn by 2 is kind of forced by that to be something. It's exactly like this. Sk, at halfway time, you have this type of random variable with sample without replacement. So there is a second coupling lemma which couples a hypergeometric random variable with a Gaussian of the same mean. You subtract the mean and then couple with a Gaussian of certain variance, square root n by 4 in this case, in such a way that this exponential moment is bounded. Once you can control exponential moments by Chebyshev inequality and so on, you can control probabilities. So these are the two key coupling lemmas that Chatterjee uses, and this is really the heart of his univariate coupling lemma. So he does this by what are called Stein's methods. Okay, so what is it that we are adding to this? Okay, so what is it that we are adding? But again, if there are any questions, I can pause. Sorry,
I don't see any questions on the chat. So,
oh, you are okay. So sorry, I moved windows. Okay, so I'm back. Okay. So these are the lemmas. So what are we doing? So the way he goes about it, I cannot explain that. That would take longer. So the whole point is we have somewhat simplified this method. This requires quite somewhat sophisticated analysis. Our analysis is that there is a simple idea. So what is at the broad level, our idea is, okay, use Cauchy criterion. What do I mean by use Cauchy criterion? Suppose you have xn goes to x, okay? So actually I have written to show xn goes to x. Suppose you have some real numbers. Suppose you know xn converges to x and you want to know how close xn is to x. The one way to show it is you can try to estimate the difference between xn and x. But another way is you can try to control xn and xn plus 1 difference or xn and x2n difference, because you can sum this up. Suppose you show xn minus xn plus 1 is bounded by 1 over n square, then you can sum it and say that xn and x are 1 over n close. Or if you can show xn and x2n are 1 over n to the epsilon close, you can show that xn and x are also 1 over n to the epsilon close. So the Cauchy criterion is that instead of comparing the pre-limit objects to the limit object, you compare it among themselves. Why is this useful? In probability, this can be very useful. You see what happens in central limit theorem. We have some things like binomial converging to Gaussian. Now, binomial is a discrete object. Gaussian is a continuous object. There are different types of beasts. Sn is, when you compare Sn to Z root n, in some sense, you are comparing like with unlike. But it's much easier to try to compare Sn with S4n. So the correct way to is you want to have the same variance and mean. So you compare 2Sn with S4n. If you can show that 2Sn and S4n can be coupled together very close to each other, then you can also compare, then you can couple Sn with S4n by 2. Then you can couple S4n with S16n by 2 and so on and keep doing that. And so finally you can couple Sn with Gaussian. That's the whole idea. Okay. So this is the idea. So, and why it should work, because when you compare binomial with binomial, you may hope for, these are all finitary objects, right? So you can hope for purely combinatorial proofs, or in this case, we use the proof using finite Markov chains. Okay, so it allows to simplify this proof strategy. This is the broad idea. Once you take that, it considerably simplifies. In fact, as I said, I was able to simplify somewhat combinatorial and analytic. Of course, whether I have simplified is for others to say, but at least Chatterjee told me that he liked some of the ideas. Okay, so what would we do? Instead of the binomial and hypergeometric coupling lemma, I will show you the lemma that I proved. Here you are comparing binomial with Gaussian or hypergeometric with Gaussian. Instead, we prove lemmas like this, that you compare 2Sn with S4n. You can couple 2Sn with S4n so that an exponential moment is bounded and these things are uniform in n. Okay, and the second hypergeometric lemma is similar. You compare, basically these things are, where I had to write Sk hat, I have written Wk. Wk of Ns is what I call Sk hat of Ns, S hat Ks. But I don't want to go through the statement here, but basically you are comparing that with a box with 4n coupons and a box with 10 coupons. So you compare these objects, finitary objects, and that gives the hypergeometric coupling. Okay, so this is what we need to carry out. How we carry out, if you can prove this, then you can prove that. So that's the idea. Now, how do we prove this? This is where the idea is. So what Chatterjee uses is he invokes, as I said, maybe I don't want to get into that. So it is somewhat sophisticated situation where you have to construct certain measures as solutions to something. But here it is much easier. We are working with finite Markov chains. Okay. So the idea is like this. The general strategy of coupling is like this. So I have two probability distributions on integers. For example, alpha can be the probability distribution of 2Sn and beta can be the probability distribution of S4n. What I'm going to explain is the binomial coupling lemma proof. Okay, so that's all I want to explain. And then similar but a little more work requires needed to go to the hypergeometric coupling lemma. Okay, so let's say alpha is the distribution of 2Sn and beta is the distribution of S4n. What we need, but it's not exactly correct, because the way we want to get a coupling of these two distributions. The first step is to find some Markov chains for which these are the stationary distributions. Okay, I want two Markov chains on integers such that one Markov chain has stationary distribution alpha, the other Markov chain has stationary distribution beta. Now, is that possible? Actually, there is a slight problem. If you look at something like S4n takes only even values. So it leaves gaps. You cannot have nearest neighbor Markov chains whose stationary distribution is S4n, but if you divide S4n by 2, it takes all values in -2n to 2n. So you can find there is a Markov chain, which I will show in the next slide, which has that stationary distribution. It is called the Ehrenfest chain. What about 2Sn? 2Sn also, now since I divided S4n by 2, I should also divide 2Sn by 2. In other words, I look at Sn, but Sn has gaps. It will be odd or even depending on n. So we just modify it by adding one random variable, which takes values -101 with probabilities 1/4, half, 1/4. So that is just to kill the gaps or the periodicity, so to speak. So, but this doesn't change Sn much. It is just a coupling of Sn with Sn plus R by just one difference. So it suffices to couple half S4n with Sn plus R. That's what we try to do. Okay, so that's what we try to do. But what are the Markov chains with these distributions as stationary distributions? Okay, that is described in these examples. Before that, let me explain that these are all Ehrenfest-like chains. So what is an Ehrenfest-like chain? So an Ehrenfest-like chain is a Markov chain on integers in continuous time whose rates of movement are given like this. There is a function of the current state, t of I minus I with that and t of I plus I. So what do I mean by that? So if this is a Markov chain in continuous time on integers, so if at the current location you are at location I, okay, so if you are now at location I, in a short time h, where will the Markov chain be? It can go to I plus 1 or I minus 1. What are the probabilities with which it will go to I plus 1 and I minus 1? To I plus 1, it will go with probability t of I minus I into h, where h is a small parameter, and it goes left with probability t of I plus I times h. So such a chain is called an Ehrenfest-like chain. One can characterize which distributions alpha will have will have an Ehrenfest-like chain whose stationary distribution is alpha. Okay, so this, if you can find such a T, this is called the Stein coefficient of this distribution alpha. Okay, so again, examples will help. So if alpha is the distribution of half S4n, which is what I looked at in the previous slide, half S4n and Sn plus R, right? If you look at half of S4n, that's basically a binomial distribution scale, and it turns out this is the what is called the standard Ehrenfest chain. What it does is T of I is a constant here. So in other words, its state space is going from -2n to +2n. Okay. Do I have 4 minutes or 5 minutes still?
Yeah.
Okay. So the state space is -2n to 2n, and you go with the transition probabilities or transition rates are 2n minus I and 2n plus I, depending on where you are. So if you are at 2n, you will only go to the left. If you are at -2n, you will only go to the right. But in between, you have probabilities to go to the left and right. So this is the standard Ehrenfest chain. So that is the one whose stationary distribution is the distribution of half S4n. Now Sn plus R is also is some probability distribution. What is the Ehrenfest-like chain for which it is the stationary distribution? With a little bit of work, one can work out that it is a Ehrenfest chain with a different Stein coefficient, which looks like this. What you need to pay attention, okay, there is an explicit formula. This is all going from, yeah, so I did it from Sn plus R. This Sn plus R goes from -n to, sorry, I should have probably written -n minus 1. Sorry, yeah, it goes from -n minus 1 to n plus 1. That's the full support of Sn plus R. And this is the explicit formula. There is a slightly different formula for the odd ones and for the even ones. But the point to see is that this Stein coefficient looks very close to this Stein coefficient. 2n, it's the dominant term is 2n in both cases. That is the key point. Okay, so the two Markov chains are pretty similar. Now, what is it that we prove about Markov chains? Okay, I will not explain this relationship to. So the general theorem that I prove is that if you have two distributions, alpha and beta, alpha and beta are two distributions, and suppose you have two Markov chains with stationary distributions alpha and beta, and both Markov chains are, let us say, Ehrenfest-like. So that means they come with some Stein coefficients T and S. So let's say alpha and beta are stationary distributions for some Markov chains, which are Ehrenfest-like with some Stein coefficients, S and T, whatever it is. Then we can construct how do we couple alpha and beta? The idea is to construct a Markov chain on Z2 whose stationary distribution will have marginals alpha and beta. Okay, the stationary distribution of the joint chain will be the marginal, will have marginals which are the original stationary distributions. And the coupling is the most natural coupling that you can think of. It's impossible to understand what is written here. It's just written so that for precision, but it is explained here. So from this is a Markov chain on Z2 that you have to define. So it goes from ij to either I plus 1, j plus 1, or I plus 1, j, and etc. These possible places. And the overall idea is that as much as possible, try to go together. Okay, so from ij, if both can take a positive step, you do that. Now, it may not be exactly possible to couple. With the remaining probabilities, let one go positive, the other will stay, or the other goes positive, this one stays. Or you try to make both go negative with as much as possible, and with the remaining probabilities, they go this way. So they never go in opposite directions, by the way. So it never happens that I goes positive and j goes negative. That would be like here or here. So this kind of coupling is all we need. And what I prove is that that kind of coupling will lead to a Markov chain on Z2 whose stationary distribution has marginals which are the original distributions. And this is the coupling statement that if you look at x minus y, x and y is the joint chain, the difference between them in the stationary, this is all expectation in the stationary distribution. In the stationary distribution, an exponential moment of this is bounded by a exponential moment of q, which is the difference in the Stein coefficients. So if the Stein coefficients are close, then the random variables x and y are also going to be close. This is the idea. So this q is what you need to make sure. So, and this is the last part. So going back to the example I had where alpha was the distribution of half S4n and beta was the distribution of Sn plus R, we already computed that the Stein coefficients for one is the constant to n, for the other it is this T of j, which is given like this. So you can, what is this Q? S minus T is pretty small. Q is, if you look at Q, it is basically, if you take T of j minus S of I, it is something like, it gives you this basically j squared by n plus 1 plus a constant. So in other words, Q is bounded by 2 plus y squared over n plus 1, which has exponential tails, uniform exponential tails. And this is what gives you that the difference in x and y also in the stationary distribution has uniform exponential tails. And that is the binomial coupling lemma that I had stated, that the 2Sn and S4n can be coupled so that uniform exponential moment is bounded. Okay, so that is the whole idea. Okay, that's all. Thanks.
Thanks, Manju. I don't see any questions, and also the time is up. We had started also late. So nobody has put a question either on the chat. So let's thank Manju for this excellent talk and very interesting idea.
Thank you. Okay, I will stop sharing that.
Okay. All right.
Okay. So is there another talk in this session or is it in?
The general public talk by Raghunathan now.
Oh, I see. Okay.